Hello everyone, I would like to share with you today something very nice, the Riemann zeta function formula for the entire complex plane. Okay, I will show you how to calculate a center point of the zeta or eta function spirals on the complex plane. I'm using the eta function spirals to find the formula for all the center points of any spiral on the complex plane. Okay. This idea is based on my previous idea about the center points of the zeta function. If you are not familiar with the idea, I recommend you to watch my other video on the YouTube channel. I will show you how I came up with the formula. This is the formula. Let's enlarge the page. Okay. This beast of a formula will give you the Riemann zeta function for the entire complex plane, both a convergent region and divergent region, on all region. Okay, this is not like the analytic continuation. Sorry, by the function. By the functional equation. I'm not using a reflection here from the convergent side to the divergent side. It basically is for the entire complex plane. Okay, let's start. I will show you first. Let's see. Let's start with the zeta convergent case. Okay, it seems fair. Okay, this is the first 100 steps of the series, convergent area. It's above real part of zeta function, part 1 of zeta function. Okay, this is the convergent value. If it will continue to infinity, you eventually the spiral will converge to I don't know, zeta 0.63 minus 0.42i. Let's see another one. Divergent case. Okay, same idea, but this is a divergent. It's going outward. This is the same value of the functional equation. It's a divergent series, and if you will change the direction, show you 1 second. The idea is to do something like that, decreasing. Okay, as you can see, it should have been a divergent case, but if we'll switch the direction, the behavior will be just like a convergent point. Okay, but at 1, because it's acting like a vector, it stops at 1. But you can calculate how to get from here to here without using the functional equation, and that's what I'm going to show you. Okay. Just want to say that the easiest way is to use the eta function. I don't know why people love the zeta function. I love the eta function. Okay, the eta function is something that I love even more from the zeta function. Okay, let's do first a convergent case. I want to say that. Okay, you have there is a spiral. As you can see, it has two arms because of the minus plus swapping. This is the convergent point. Again, if the series would have continued to infinity, this is the point, this is the value that you will get. But what about the divergent? How to get the divergent part? Okay, I would like first, I know some of you know this already, some of you skeptical, but stay with me. I guarantee you that it will be very nice to see something on the center point file that I'm going to open next soon. Divergent case, let's see. Okay, this is a divergent case when the real part, no, I want first, okay, no, I want first the fixed radio case. Okay, fixed radio case. Okay, real part of eta function is 0. Okay, as you can see, there is a fixed radius. This is the point where the convergent part is, before it going to divergent, it's like a barrier. It stays on a fixed radius. Okay, this is easy to calculate this point because what you need to do to get the radius, you just need to get the imaginary part. 1 over the imaginary part will give you the radius. But we want the center points for all the complex plane. Okay, so now I'm going to open the eta function divergent case. Very important to understand this case. Okay, I'll make it stop. Okay, the idea is like this. As you can see, we have spiral that's going outward, and it has two arms. Okay, this is one arm and this is the other arm, and basically to calculate, to get to this point, the idea is to do something like this. I will take this point and I will take this point. Okay, I will sum both of them together and divide it by 2. Okay, and I'm going to take another point from here next to it and another point from here next to it and divide it, that point as well, by 2. I will sum first the both and divide it by 2. Okay, what it will give me, many points around here. Okay, swirling around the analytically continuation value, that the center point basically that I want to get, and after that I will take it will create here another spiral. Sorry, I shouldn't have done that. It will create another spiral. Okay, so basically what I'm doing, I'm taking the average of two coefficient values of the eta function on 2 different arms every time. Okay, you will see in a minute. Okay, let's okay, let's open the center points. Don't save. Okay, let's go. Okay, base file. I know this is not the what people are used to see in math, but this is the way I love to write stuff. I know some of you won't like it, but it's how I like to write stuff. This is clear to me, not to someone else, but it's clear to me, and this is how I like to work. So sorry about that. I will try to be as clear as I can. Sorry about my English. I will try to make it clear as much as I can. Okay, base spiral. Basically, level 0 is the eta function. Okay, this is the summation of from the first value to a x value, whatever x you want. It doesn't matter. The more x is larger, the more accurate it will be, but it doesn't matter because we are going to infinity in the end without that specific x, so the x can be whatever that you want. Okay, this is the point. Let's call it arm 1. It's not arm 1, but like I said, I'm writing stuff because in my mind it's easier for me to get it. I know some of you won't like the way I write stuff, but I'm sorry. But try to understand what I'm trying to explain here. Okay, arm 1. Okay, let's go here. This is arm 1. You see, arm 1. So zoom out. Arm 2, arm 3, arm 4, arm 5, arm 6, arm 7. It's like it's not the arm. Think of it as like I don't know. All the arm with odd value, it's on really arm 1, and all the even value of arms, it's on the other arm. Okay, if you want to think about like that. Okay, what I'm basically is doing, first of all, let's write it like fx plus 1, fx plus 2. You get the idea. What I show you right now, this is the screenshot. Okay, we are going to do average on every 2 consecutive arms or values or in the series. This way we will create a new spiral that will rotate around the central point we are looking for. Okay, like I said earlier, I'm taking arm number 1 plus arm number 2, okay, and divide both by 2, and I will get a new point. Let me zoom here. It will create a new point here. The point is level 1 arm 1. It's a shortcut. It's a short L1, but it represents level 1 arm 1, a new arm 1 dot. Okay, from arm 1 plus arm 2 divided by 2. Okay, and the dot, I think, sorry, not them. Okay, this is the point. Okay, let's zoom out even more. Come on. Okay, arm 1, arm 2, divide, it will give me a point here. Here, okay? Same goes for the rest, okay? Let's go. Okay, all the green points, all 6 green points. I started from 7. I can go as many as I like. It's just so you can understand the idea. Okay, I'm started from 7. Okay, and those 7 points give me 6 new points of average. 1, 2, 3, 4, 5, 6. This is another spiral. Let's do the animation, maybe it will be clearer. I don't want to touch the P. And start. Okay, you see, it's a spiral. It's moving. Okay, this is not the original value of the eta function. The original value of the eta function is, let's zoom out. Come on. Okay. You see? Okay, this is the original eta value. Okay, and I took the point, of course, a real part is a half, and the imaginary part is 14.4725, the 0 point. Okay, the 0 point, and it's that value is going to infinity, and because we have I don't know what 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, I think, digit, then it's not a complete 0. And my value in the end will be more accurate than this value. Ironic, but it's not ironic. It's 2 to the n, so it's logical. Okay, let's stop the animation. Okay, so I have a new spiral, level 1, and again the same idea. I will divide every 2, okay, by 2, and it will create another spiral. You see, we are only at at level 2 spiral, and the analytically continuation value that the program gives me is way off already. Okay, let's go. Okay, this is the level 1 spiral. It's a new spiral. Okay, same idea, but a new spiral. Okay, you see, and it will create another new spiral at level 2. The same idea. I'm taking the level 1 arm 1 plus level 1 arm 2 divided by 2, and I'm getting a new value. This is the new value. Okay, let's go to level 2. The same idea. Okay, the same idea. Okay, let's zoom here. It's the same image. Okay, the same image. Okay, I hope you are following me on my thought line. Let's see. Okay, level 3 arm 1. Okay, do you see a pattern here? I think it's obvious, but we are going to try a few more. New spiral, level 3, the same idea. Okay, look, it's pretty obvious. Okay, new spiral, level 4, same idea. Level 5 arm. Okay, never mind. Okay, I think we got the idea. It's going like that for infinity, of course. Okay, level 4 and level 5. I think I will stop here. Okay, general summation formula. Let's take all the arm1 of every level. Okay, binomial coefficients. New spiral at level n-1. Okay, I think it's pretty obvious what you see here. Never mind. I wanted to show you something, but never mind. I know that I can go from here to write this line. You can skip what I wrote here, but just to set the mind at ease, the center point need at least 2 arms at level n-1, so there will be a center point at level n. Basically, I'm saying we need an even number at least, so we can divide. This is the spiral at level n. Okay, any n. And this is a number, and we're going to say it will go to infinity in the next line, in the next page. Okay, this is the formula for the center point, but only when I will add the going to infinity part. Okay, this is our original fx function. Again, x can be anything you want, 10, 11, another n if you want. Okay, and you will get something like that. Okay, you can put some other value, rearrange, you can play with the formula. I have a nice, very nice idea how to change the formula. Maybe I will do a video soon about what kind of a nice way and tricks you can play with that formula, but it's not for now. Okay, let's rearrange. Okay, this is the formula for the eta function for the entire complex plane. Okay, as you can see, this function is, sorry, I want to show you guys something. I think it will be more clearer. Okay, for the convergent side, this is the convergent side. You know how to get to the point, and for both divergent cases, or for those cases when the real part of eta is 0 or the real part of zeta is 1 and above and below, sorry, and again for the eta below 0, for those cases are divergent case. And to get to the center point, which is the analytically continuation, basically you need to use the functional equation to do a reflection from the convergent side to the divergent side. What this formula is actually doing, you are not using any reflection. This formula will give you the convergent, because I'm reversing the, sorry, here. I'm reversing the direction of the spiral of the divergent case to behave just like a convergent case. So basically, you will get the formula for all the entire complex plane. Okay, this is for the entire complex plane, both convergent and divergent, without reflection, and the divergent side will give you the analytically continuation values, the same value as the functional equation. Basically this, or this, if you want the eta function, but this is the zeta function. Most people will want to use, I think, this function. This part is equal to the zeta function on the functional equation, okay, analytically continuation value, if you want, if you are using the divergent side, okay. You can see it's some funny stuff I wrote here. You can make the s value to be 0, and all of this will be 0, and you will have a summation of -1, 1, -1, 1, -1, 1, -1, 1. So the summation will be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. If the first value will be 1, the second value will be 0, 1, 0, 1, 0, okay. So basically it will equal to this, and the summation in the brackets is 2 over n minus 1 divided by 2 to the n, and you will get half. The other way, on the other case, when the first value will be 0, this is going to be 1. You will get this. It will be 0 as well. I would like also to show you, not only for the 0 point, but that is working for all, the center point is working for all the complex plane. Let's go to the values that most people know. Let's set the imaginary part to 0, and let's go, let's say 1. Minus 1 is good. Second, just a second. Okay. Okay. We are not even at level 3. Yeah, I think you get the point. Let's go. Zoom out. Oh, come on. It will take forever. Let's do -2 on the 0. It needs to go to the 0 point. Come on. Okay, this is fair. Analytically continuation on 0. It's using the sinus in the formula. And this is the center point. Let's go out. Should be a very large number. Okay, this is level 1. Yeah, I just want to point out this is only the first 1000 steps. Okay, so not going to infinity because we're only at 1000 steps. Come on. Okay, 500,000 seems right for the okay. This is the eta function, level 0 if you will, and I'm zooming in. Level 1, come on, level 2, this is going to take forever. Okay, I think we got the idea. Okay, let's check something else. Just want to show you that it will work for any value. Let's do 0 point of the eta. It will be half. Okay, this is reach for half really fast. So I need to divide. No point to show that. No. Let's take another example. I don't know. Let's the function calculator. High accuracy. Let's try. Let's check for minus 1.2. Oh, sorry, 1.2. Execute. Okay, looks okay. 0.196. Okay. Come on, this is only for the 1000 steps, okay? The base, the level is 0. Okay. Okay. Looks legit. Okay, let's zoom in. We're going to level 1. And now for, you know what? Let me, without the analytically continuation part. Level 2. Come on. Level 2. Level level 3, level 4. Sorry, I'm pretty close. Okay, 1.969. 0.196953. 53. Accurate. Maybe it's doing a complex. Can I add something like 2i here? No. Pity. I can use that this algorithm to calculate the complex plane easier, and it will be very accurate. Using this, it will be very accurate. With the I mean, with the complex value. Maybe we'll try another one. I don't want to make a huge divergent spiral because the value will be Just the zooming in out part will take me like forever. Let's do -5. Sorry, -5. I call it. Okay, -5. No, I want something more. Okay, I will show that, and afterward I will not something that nice. I want something that's not nice. Okay, to fit. Oh, level 4. Wow. Wow. Okay, this is, I'm not going to zoom for this number because this is insane. Okay. The number here is, whoa. I can maybe I will change. It's still huge. Leave it. Still huge. Okay, let's. The X can be whatever. As a metal. No. And it's 1. It's not good. Okay, the number is way. I need a few more levels to reach to the value that we want. -3.3. Looks okay. Oh, sorry, forgot the analytical continuation. Okay, you see, very nice. Come on. Take it to 1000 and nice. Can add another more level. Nice. Okay, do you see that? Let's, sorry. So it will be on him. Okay, you see, this is level 5. Of course, it's going to infinity. So level 6 will be closer, closer, closer. Okay. Okay, let's delete. Don't need the level 5. This is not only for the divergent part. I can also, it's going to its fit to the entire complex plane. So I can go for 1.1. You know what? Let's do something nice. 1.6. Okay, close to the critical line. This is a divergent case, but think I want to show with not using a reflection. And, sorry. This and this. Okay. Let's okay, first I will show you that 0.623. Nice. Only level 1. Look how accurate and nice it is. And turn off the analytical continuation. Come on. And let's turn it back on. Nice. Very nice. This is what I wanted to show you. Let's do one more on the complex plane. Let's change the B to something else. Let's do the animation. Too fast. Stop. Let's turn on the technique continuation, that you will see the center point is really on the spot. Okay, you get the idea. I'm pretty sure you get the idea. Come on. Oh, it will take forever. Let's do one too close to the zeros. I like the zeros. We want close. We don't want the 0, but we want close to the 0. 14.15. It's not the 0, but it's pretty close. You know what? Let's change it to something near the 0, so you can see. Oh, come on. It's getting close to the 0. Let's do the animation. I love the scrolling part. Oh, wow. Let's go. Nice. You see? I told you. Spiral. Another spiral. Near the 0. Now getting close. Get closer to the 0. Stop. Let's do the animation. A little. No. Let's go back. Too much. Oh, come on. Okay, seems okay. I want it to be a much slower speed. 1.1 should be okay. And let's go. Let's like jumping. I don't want the jumps. Speed, once. Maybe like this. Smoother. Okay, let's stop. Let's adjust the values. Seems okay. And let's go to here. too far. Sorry about that. Still no? Oh, come on. This is a bit slow. I want it slow, but not that slow. Increase the speed. No, it's jumping. I want it smoother. Jumping. Come on. Come on. Maybe this. Okay. This should be fine for the animation, and I want you to see the spirals. Okay, this is when it's not rotating. You see all the spirals? Okay, now we'll do nice. And 0. And it's working around. Pretty close. Okay. Do you see all the spirals? Nice. Okay, let's stop the animation. Okay, I think it's pretty obvious what I wanted to show you here. Tell me what you think. Okay, nice formula. Goodbye, stay tuned.